Hello and welcome. I am Harjit Singh. I'm here to discuss the basics of statistics. And today's topic is about probability distribution. So we will be talking about the basic concepts related to statistical probability. So today's learning objectives include defining key probability terms like probability, experiment, event, and outcome, and assigning probabilities using classical, empirical, and subjective approaches. We will also learn how to determine the number of possible outcomes using counting principles like multiplication, permutation, and combination. And then we will learn how to calculate probabilities with the rules of addition, um, means mutually exclusive and general, and multiplication, including independent and dependent events. Finally, we will learn how to utilize tools like contingency tables and tree diagrams for computing and organizing probabilities. Let's dive into this. So what is probability? The very basic definition of probability. What is the probability? Probability means likelihood in English, likelihood. So the likelihood of an event occurring, well, the likelihood means the event may or may not occur. If it occurs, then the range is between 0% and 100%. So 0%, 0 divided by 100 is 0, and 100 divided by 100 is 1. So basically, probability falls between 0 and 1. Okay. When we say probability is 0, right, that means most certainly that event will not happen. Okay. So the value of 0 and 1 are inclusive. Be mindful of that. So 0 less equal than p less equal than 1. So 0 means absolutely it cannot happen, and when it's 100%, that means it's sure to happen. In between, the likelihood changes. In the middle, if you see in the middle, the chances are like 50-50. So for example, a chance of a head in the single toss of a coin. So when you toss a coin, like one experiment, single experiment, the chances of head or tail, they are 50-50, right? And depending on what we are doing, the probability will change. So for example, here is 0.2 low probability. It's not 0, it's not middle, it's not high, it's low, 0.2, 20% probability. It says the chance Slowpoke will win the Kentucky Derby. So this could be any other event where, based on the data available, that there is low probability. And then in another scenario, the probability can be high. So 70% of chance of an increase or in federal taxes. So this is a scale of probability from 0 to 1. All right, so what is an experiment? Because when we talk about the probability, this is based on experiments. So every time we do something, we do some experiment, there is probability of some outcome this way or that way. So what is experiment? experiment is something that leads to specific outcomes, right? So when you do something and it will produce some outcome, and outcome is the result of the experiment. That's the second definition, outcome. Okay, experiment is a process. There's some steps you perform, right? And when you finish doing it, it produces some result, and the result is called outcome of an experiment. Now, event is a collection of one or more outcomes of the experiment. Here's an example here to illustrate that. So again, going back, this is a die. This is a die. Die has 6 faces, right? 6 faces. So 1, 2, depending on how many dots you, depending on what face shows up. So 1 means 1 dot shows up, the face that has 1 dot, like this side, that shows up. 2 means a face of with the 2 dots show up, and 3, and so on. So the maximum dots that any face of the die has are 6. So the possible outcomes of rolling a die, right? There's 6 possible outcomes because die has 6 faces. So experiment is rolling a die. Roll a die. What will happen? So what we are trying to find out by rolling a die? Oh, count the number of members of the board of directors for Fortune 500 companies who are over 60 years of age. And that's what our intent is. And we can relate various possible outcomes to each phase of the die. So possible outcomes here. So we have 6 phases. So when we observe a 1, that means that none is over 60. If the side with 1 dot shows up, that what does it mean? This means that nobody is over 60. And if a side with the 2 dots shows up, then 1 is over 60. So each phase is related to a possible outcome. Okay, this is predefined. So this is this example of some possible outcomes. Possible events. What is event? Event is a collection of 1 or more outcomes. So out of these 6, actually, this is something that we can study here. Some possible outcomes. Basically, what we are looking here is in this experiment, observe an event. Observe an even number. This is what we want to do in this experiment. So observe an even number. Okay, how? Observe a number greater than 4 and a number 3 or less. Okay, and it has to be even number. Okay, so what does it mean is like this is a 4. So a number greater than 4, which is even, that means is 6, and number less than 3, that is even, is 2, right? So we're going to look at 2 and 6. So if we get 2s, so how many of these? We know that actually these are the possible outcomes, and based on the data we have, we can see, okay, when we conduct this experiment, we find more than 13 people are, members are over 60, and fewer than 20 are over 60. So this number 3 or less represents over 60. So 3 or less means 2, and we know that 2 is about over 60. So in this sample experiment, 20 are over 60, right? Fewer than 20, sorry. And the other one is about even number here, 6. 6 is like how many are over 60? So more than 13 are over 60. So, okay, there are 3 approaches to assigning probabilities. First one is classical approach. Second one is empirical approach. Third one is subjective approach to assigning probabilities. So what is a classical probability approach? Classical probability approach assumes equally likely outcomes. How we find it? Using the classical probability approach. So probability of an event is equal to number of favorable outcomes divided by number of all possible outcomes, total outcomes. Let's look at this example. So we have 6 faces of die, right? 1 dot, 2 dots, 3 dots, 4, 5, and 6. 6 faces of die. So example is, okay, roll a die, 6-face die only once. What's the probability of obtaining even number? So how many faces has even numbers? There's 2, there's 4, and there's 6. So 3 faces out of 6, they have even number of dots. So number of favorable outcomes, that are the possibility of total outcomes that are even. That's a 3. And how many total? Total sides are 6. So number of favorable outcomes are 3 that we are looking for. And all possible outcomes were rolling a die is a 6 sides, 6 faces. So divide by 6. So for this example, probability of an event to get an even number after rolling a die is 3 divided by 6 is 50%. That's a classical probability approach. In general, there are 3 formulas to find number of outcomes: multiplication, permutation, and combination. Let's look at them. For multiplication, if we have m possible outcomes of one event and n possible outcomes of another event, there are 2 events, right? So how many total number of arrangements that is possible with the 2 outcomes of these events? So n times m, you multiply them. We can, this is only for 2 possible, two events. If we have more than 2 events, multiple events, we can use the same approach, multiply. For example, the example here is a pick 3 lottery, the name of the lottery basically, where 3 tumblers, each with the balls 0 to 9. 0 to 9 means a total 10. After tumbled, 1 ball is selected from each. What's the number of possible outcomes? So basically what we're looking here is now with 3 tumblers each. So there are 3 tumblers and each with the balls 0 to 9. So 10. So the possible outcomes are 10, right? With the 3 tumblers. So now So what are the number of possible outcomes? One wall is selected from each. So there are total three possible ways to three possible outcomes. So you multiply for each ball, we have 0 to 9 possibilities, right? So total 10 for each ball. So 10 times 10 times 10, 1/3 possible outcomes. How about permutation? Permutation requires things to be in order. So it requires some order. So an arrangement of R objects selected from a single group of n possible objects. If there are n possible objects, you want to make create four. I mean, so n possible objects, but you wanna make arrangement of R possible out of n, total n, right? In that case, we use permutation. The formula, the symbol we represent is small n, capital P, and a small r, NPR. So this n with a sign of exclamation, we call it n factorial. N factorial divided by n minus r factorial. So to expand this, this is the way to expand factorial. N times n minus 1 times n minus 2, and so on, expand it like to all the way, depending on how many, the value of n it is, and the value of r. And divide by n minus r factorial. So let's look at the example. Example is a media company is producing a 1-minute ad video. In the production process, 8 possible video segments were made, right? 8 different video segments are made in production. Now, but they have to select only 3. They have to select 3 segments out of the total 8 they have made. How they do that? Out of 8, how many different arrangements of 3 segments are possible? That's the question. How many different ways can the 8 video segments be arranged? So it has to follow certain order. So n is total 8. That's the total number of possibilities we have. The total outcomes are 8, because the 8 different video segments were made. But they wanna have arrangements of 3 out of 8. They're gonna have like 3 possible arrangements of the 3 outcome segments. Okay. So we can use this formula, permutation formula. Here n is 8 and r is 3. Simply replace the numbers with the values. So 8 is 8 factorial divided by 8 minus 3 factorial. So you keep opening up 8 until you go all the way, right? 8, 7, 6, 5, using the formula before. So the reason we stop at 5 here is you can go all the way, but because in the denominator we have 5 factorial here. So if we can open 5 factorial also all the way, but there is no need, because we can 5 factorial on top of this line cancels with the numerator and denominator, they cancel out. This cancels out. So we can stop here. What we have remaining is 8 times 7 times 6. So total number of ways, 3 segment selection that's possible out of total 8 possible outcomes. So it is 336. Now, there is another way to do that is called combination. In combination, when we make arrangements, the order of the selected object is not important here. Order is not important. They can be arranged in any way. Like, for example, ABC can be BAC, doesn't matter. Formula for that is NCR. So n factorial divided by r factorial times n minus r factorial. Let's look at an example. Example says the Grand 16 movie theater uses teams of 3 employees to work the concession stand each evening. There are 7 employees available to work. Okay, so 7 employees available to work. Out of 7 employees, it has to use teams of 3 employees each. Okay. Here, the teams can be formed in any order, doesn't matter. Randomly picking 3 out of 7. How many different possibilities are there? Okay. How many different ways can be done? The formula, combination formula. So n is 7, total number of employees available, and 3 is the size of the team. So we get is when we process this factorial relationship, we got 35. All right. Second approach for probability assignment is empirical probability assignment. So what is the empirical probabilities approach? Based on observed data and the law of large numbers, which states that empirical probabilities converge to the true probability as the number of trials increases. And the key thing here is the law of large numbers. We will talk about that. So the formula for that, this is the formula. Empirical probability is based on relative frequencies. So how we find relative frequencies? We saw that in another video also. So number of times that any event occurs divided by total number of observations, right? And we will look at the example to understand more clearly. So number of times the event occurs divided by total number of observations. Okay, let's look at an example here. And as I said, no law of large numbers applies here. So what is the law of large numbers? Says over a large number of trials, the empirical probability of an event approach its true probability. Basically, the more, just like buy lottery ticket, the more you buy, the more probability you have of winning. So so it says that as the number of trials increase, the probability increases. Here is example here. So number of trials, if it's only 1, the possibility of number of heads is 0, and the relative frequency is 0. Means 0 divided by 1 gives you 0, right? And when we have 10 trials, the number of heads possible, and these are assumed values here. So 3 divided by 10 gives you 0.3. So when we increase number of trials to 50, we get 26 number of heads possible. So 26 divided by 50 is 0.52. and you keep going, keep increasing number of trials. As you can see that number of heads, the the chances of getting number of heads keep increasing. So same thing is with the relative frequency, it keeps going up. As you approach 10,000 number of trials here, and number of heads possible is 5,027. 5,027. So when we divide 5,027 by 10,000, it gives you about 50% chances here. So this is when we say divide the number of heads with the number of trials, this is the formula we are applying here. Number of times the event occurs divided by number of observations, like this one. So number of times this event occurs divided by number of observations, right here. Here's a real example here. Standard & Poor S&P 500 stock index was down 4 times over the course of previous 20 years. What is the probability that index will be down next year? So we need to look at the probability per year and then use that understanding. So now let A represent the even, the even of a negative yearly return, right? Not even, actually, this is event. This is a typo here. So A represents the event of a negative yearly return. So number of times the event occurs divided by number of observations, right? So what it's saying is like this is okay, 4 times he says the Standard & Poor 500 stock index was down 4 times over the course of previous 20 years. So it was down 4 times. Okay. 4 is given to us. So that's the number of times the event occurs, 4 times. Total number of years, 20. So 4 divided by 20, it gives us 0.2. So because we are looking at, so this is a probability of this happening per event. So if we have to speculate that, okay, what is the probability that the index will be down next year? That will be 20%, 0.2. Third type of probability assignment is subjective approach. What is this? It says that probabilities are assigned based on personal judgment and available information. Okay, if there is no experience, there is no data available that you can use to base the probability, then the subjective approach is used. So somebody would assign the probability based on whatever information they have available. To sum up, these are the 3 approaches. So basically, we were talking about approaches to probability: objective versus subjective. Then we have 2 for objective and 1 for subjective. And objectives, we have classical and empirical probability approaches. And subjective, we have based on whatever information is available to us. And classical probability is based on equally likely outcomes, and empirical is based on relative frequencies, as we saw in previous examples. Now let's look at the rules of addition. Okay, The underlying concepts are mutually exclusive and collectively exhaustive. What is mutually exclusive? It says that occurrence of one event means none of other events can occur at the same time. So possibility of one occurrence rules out the possibility of another occurrence at the same time. How about collectively exhausted? It says that at least one of the possible events must occur. Okay, when there's one of the possible events must occur when experiment is undertaken. Okay, so for example, in a fruit basket, at least one fruit must be there. Now, if the events they are mutually exclusive, that means possibility of having one rules out possibility of the other one, either this or that. That's what it means. So or B. So the way we write a mutually exclusive type of relationship here is P in parentheses A or B. Okay, probability of A or probability of B. Both cannot happen at the same time. So since this is the or relationship, we write here PA plus PB. When we have plus sign in between, that means either or. If you take 680 freeway, you are not taking 80 freeway, for example. There are two freeways. Okay, rules of addition. Now we have an example here. A machine fills the plastic bags with a mixture of beans, broccoli, and other vegetables, and most of the bags contain the correct weight. But these are the observations here. So some variation is there. Underweight, so there are three different variations: underweight, satisfactory, overweight, and different events are related to that, A, B, and C. How many packages underweight? 100. Satisfactory, 3,600, and overweight 300. Total 4,000. Now, what's the probability of occurrence? Probability we find is the probability that's happening in one event divided by total. So the probability of occurrence of underweight bags is 100, because the 100 are underweight, divided by total 4,000, so 0.025. Similarly, we find another like 3,600 divided by 4,000, 300 divided by, it gives us 0.9, and 300 divided by 4,000 gives us 0.075. And whenever we add probabilities, they all need to, individual probability, when we add them, they should all come out to be total 1, because sum of all possible probabilities of various events, it must equal to 100%, and 100% is 1. Okay. Now, what is the probability that a particular package will be either underweight or overweight? Because either this or that, not both. Either underweight or overweight, either A or C. Remember, we saw the formula here, PA plus B here. Here, same thing, A or C. So probability we have for PA underweight is 0.025, and for overweight we have 0.075. We add them up, and So to answer this question, we have a 10% probability that a particular package will be either underweight or overweight. Now, complement. Complement means if something is true, then other possibility is not true. Okay, not true. A complement. It says that probability of an event happening by subtracting from a probability of event not happening. So what is the probability of something happening? Means the total probability minus the probability of the event not happening. So total probability, you know that is 100%. 100% means 1. 100 divided by 100 is 1. So the way we represent something not happening is with a tilde. This is called tilde. The shape you see in front of A is called tilde. Whenever you write something like P in parentheses tilde A, that means probability of event A not happening. And when it's without tilde, I say probability of event A happening. So probability of event A happening plus probability of event not happening is equal to 1. That's the total probability. Okay. So probability of event A happening is equal to 1 minus the probability of not happening. So if you look at this, that this green area represents probability of event not happening. So probability of an event happening is within this circle. See circle here, gray circle. This is the probability of A happening. And if we look at the total area of this rectangle, that is event A plus event not A. So because this is sum of the circle and the remaining rectangle, right? So A plus tilde A. When we say, okay, what is A then? A is total minus tilde A. So total is 100%. 100% means 1. So P probability of A, event A is equal to 1 minus probability of not A, like this. Here's an example. The question here, this is example we saw before, remember? Right here. So now we're going to use the same thing. So what question is, what is the probability that a particular package will be satisfactory? Satisfactory, remember here, satisfactory, we have 3600, right? So we already know that the probability of something or underweight or overweight is 0.1, right? 0.1. So total is 100%. We need to find this. We already know the sum of this and this, underweight or overweight. We found this before. Total is 100%. So we can basically, we are looking for this. We can subtract the sum of the first and the last one from total 1. And that will give us our answer. So total is 100% minus in the bracket here, probability of A plus probability of C. And we already had found it before right here. And we can use this 0.10 value here and gives us a 0.90. All right, so now how about joint probability? Joint probability is where we have this kind of Venn diagram, circles. So this you see on the left hand side, the gray area here is the probability of Disney. That's the individual probability of this event. Disney is 60%, and for Bush it is 50%. And when there is overlap area here, that is both, because of both of these circles, they overlap here. So this area includes both Disney and Bush. and the given probability is 30% for this here. Okay, and this is called joint probability. When so joint probability is the probability where we have two or more events they happen at the same time. The probability of two or more events occurring same time. Okay. So how we use this? We can use this like, for example, if we want to find the probability of only Disney and only Bosch in this kind of scenario, we need to remove the common area from the joint from this, so we can have like in terms of only Disney and only Bosch, because this is joint. Joint has to be subtracted from the total. Like here, for example. So here PA or B is equal to PA. Remember, mutually exclusive is like when you don't have overlap. But now we have overlap. So you need to is still you trying to find either A or B, right? But we don't want to double count. So we need to remove the joint area, common area where we have both. So this means that if you see this PA or B is equal to, when we have a joint probability available, PA, either probability of either A or probability B, right? But we have to remove the joint probability from it. Okay, this gives us the probability exclusively in terms of A or B. No double counting. Okay, here's the example. So we have a cards card king, heart, or king of hearts. The probability total number of cards in a deck are 52. There are 4 kings. Probability of king is 4 by 52, and hearts we have 13. So probability 13 by 52, and king of hearts is only 1. So we have A, and so the A and B both. This is 1 by 52, right? So now we have to find the probability of A or B. A or B. So we need to do is like the same formula, PA plus PB minus PA and B. The joint probability need to be subtracted from it to find only for this or this. So we already have this probabilities here. 4 divided by 52 plus 13 by 52 minus this joint probability gives us 0.3077. Okay. Independence. What is independence? So independence means the occurrence of one event has nothing to do with the probability of occurrence of another one. That's independence. So probability of occurrence of one event has no effect on probability of something else, some other event. You rolled a die, tossed a coin, you had head in this experiment, one event, you had a head. Second time you toss, it doesn't mean that you will have a head again. Okay. So the occurrence of one event that you have done, like you had a head, it doesn't mean that the probability, I mean, you will have a head again in the second occurrence. Okay. Because both events occur at different times. First, you toss the coin, you had a head. Second time, you toss the again in different time. They are not happening at the same time. So It's the same coin. You're flipping it 2 different times. So the outcome of a first experiment is independent of the experiment of the second event, and right? Sorry, second event is independent of the first event. The way we write here is not or, it's and here. So 2 independent events, we write A and B. Probability of A and B. And the or relationship is uses a plus sign, and relationship uses multiplication. So PA times PB. Okay. You need to have at least 2 independent events to use this rule. So here is the example. A survey by American Automobile Association revealed 60% of members made airline reservations last year. 2 members are selected at random. What is the probability both made airline reservations last year? Okay. Because the probability here is that 60% of his members made airline reservations last year. And now 2 members, right? The 2 members are selected at random. That means that there are 2 different experiments, 2 events, and the probability of each one is 60%. Remember the formula here, PA and B, PA times BB, BB. So we multiply 0.6 by 0.6 is 0.36. Conditional probability. Conditional probability is like you have some probability already given. Something already happened. Okay, provided you have this, then what is for the other? Okay. So the way we read this here, we write here is, now we write P in parentheses B and this bar and A. So how we read this? We read this as probability of B given A. A is given. When A is given, what is the probability of B? Okay. So, and this is the formula we use here. So the multiplication rule, P, A, and B, when we use conditional probability, P, A, and B is PA, which is given, and then P, probability of B given A. A is whatever is given, you will write first. So PA is given. Now, this is given to us. Now, what is the probability of the remaining event? B given A. This is just how it's given A. That's how we write it. Now, look at the example here. A golfer has 12 golf shirts in his closet. Total 12 golf shirts. Suppose 9 of these shirts are white and the others are blue. Okay. He gets dressed in the dark, so he just grabs a shirt and puts it on. He plays golf 2 days in a row and does not return the shirts to the closet. Okay, understand this problem. So, all right. So what is given to us? So first of all, the question is, what is the probability both shirts are white? Apparently, the first day, both days, actually, we are looking at the white shirt probability. Okay, the 2 different events happened 2 days in a row. So what is the probability on first day? Remember, the number of possible outcomes divided by total number of outcomes, total number. So given is the first day. First day is given. We know first day there were 12 shirts and 9 of them were white. So total 12 and 9 of them are white. So what is the probability of picking a white shirt in this case? 9 divided by 12. Okay. So we know that we figured out for first day is 9 divided by 12. Now, so we need to consider this before we find the probability of next day. Probability of P given A. All right, so first we write down probability of W1 means white one. W first day of having a white shirt is 9 divided by 12. Because total number of white shirts are 9 and total number of shirts are 12. Okay, now this is given to us now, 9 by 12. So what is the probability of picking the white shirt second day also? Because one shirt is already picked up. Then how many total are left now behind? 12 minus 1, 11. So total number of shirts left in the closet are 11. You have to consider this. You have to remove this from the scene because one shirt is already taken and it's not put back. It says those shirts are not returned to the closet. So they are thrown in the laundry or somewhere. So total number of shirts left are 11. How about because one shirt is already taken from because we're looking for the white shirts, and assuming that the first day shirt was white and it has been taken, so how many total white shirts left behind? 8. 9 minus 1. So what is the probability now for second day? 8 divided by 11. Again, so we multiply. So PW1 is 9 by 12. P probability PW2, second day is white shirt. Given first day white shirt is already gone. So we multiply these. 9 by 12 times 8 by 11 is 0.55. Contingency table. So what is contingency table? It uses so we use contingency tables to classify and calculate joint probabilities. So what we have is a joint probabilities because we have 2 or more identifiable categories or classes. So what we have 2 classes. This is one way. One is this way in red. The other one is this way, a column, right? These are all the row headers and all column headers. Column headers are one class or category, and row header is one or other class or header or class or category. Okay. So in one what we have here is we have movies per month. It says people age less than 30, people age 30 to 60, people age like 60 or older. And depending on how many movies per month they watch, maybe some people watch. So people who 0 movies means A1, 1 or 2 is A2, and 3, 4, 5, A3, 6 or more, A4. So you name this. This is the names given to this class: A1, A2, A3, A4, and give the labels given to the ages of the people are B1, B2, and B3 for sake of discussion. Okay. So what we have is a number of people who watch 0 movies and they were less than 30 years of age or 15. Okay, and number of people age up to 30 to 60 watching 1 or 2 movies per month are 100, and that's how these numbers are. And here the bottom is total. You add them up. All these numbers added up 100. All these numbers added up to the total here, right? Now, So this kind of table is called contingency table. Now let's see how we use this kind of information. We can use this kind of information to draw tree diagrams. Tree diagrams are used for decision making, widely used. Okay. So what happens here is you start the tree diagram. This is root of the tree, age, and how many different categories we have now here. We have 3, right? This one, B1, B2, B3. So B1, B2, B3. Okay, ages. These. So what is the probability that leads to this? B1, B2, and B3. Okay. How we find that? So we have a total is 500, right? Total is 500, and age less than 30, B1 total 100, and B2 total 25, and B3 175. So how we find probability? We divide 100 by 500, 225 by 500, 175 by divided by 500. So if you see this here, so how many people are 30-year-old or younger, and this and so on. So we divide 100 by 500, 20% people. This is 45% people here, 35% people here. So we arrive here, right? Now further, we can look at the probability of each of these, okay, depending on how many movies they're watching per month. Now, okay, people who are age less than 30, B1, okay, then now from here we look at, okay, how many people are watching 0 movies, or 1 or 2 or 3, 4 or 5 or 6, right? So what we do here, we divide this number for each divided by the total. So 15 divided by 100, 25 divided by 100, 55 divided by 100, 5 divided by 100. So we have 15, 25, 55, 5. 15, 25, 55, 5, right? Divided by 100 or each of them. Similarly for B2, we do 50 divided by 250, 25, 100 divided by 225, 60 divided by 225, and so on. So we do this for this branch also. Okay, so these are the 3 branches here. So we do this for all these 3 branches here and find the probabilities. And we get these probabilities, right? See all the listed here. And they refer to, okay, whether they're watching 0 movies, no movies, or 1 to 2 movies, or 3 to 4, 5, and 6 or more for each of the age categories. And we get the complete information drawn here. And okay, so we got this up to here, this point. Now, based on this tree diagram, okay, we need to, so what is the total probability? What is the total probability for 30-year-old or younger, okay, who watch 0 movies, no movies at all? So we need to actually start from the root and look at all the probabilities in the branch and multiply them. So what we have is 0.2 multiplied by 0.515, it gives us 0.03. Similarly, okay, how many people, what is the probability of people 30-year or older or younger watching 1 or 2 movies per month? So we look at all the probabilities we have found along this line, along this branch, all the way to back to the root and multiply. So we have 0.2 multiplied by 0.25, it gives us 0.05. So we do this for everything all the way down. Finally, this is, we got all the information we need here for every single category. Okay, this is the use of contingency table and to build a tree diagram. Okay, a tree diagrams are used for decision trees, and they are very, very helpful in making decisions based on this. Okay. So this was a discussion on basics of a probability in the statistical area. I hope you enjoyed this session. If you have any questions, let me know. Otherwise, I'll see you in some other session. Thank you for your attention. All the best. I talk to you later. Thank you. Bye.